Chapter 7 is on rational expressions. Chapter 7 is on rational expressions. Section 7.1 is Introduction to Rational Expressions. We notice that a rational expression is just a quotient of polynomials. So essentially p of x divided by q of x, where p of x and q of x are both polynomials, and q of x isn't 0. So we notice that the stereotypical rational expression is something like 3x minus 1 divided by 2x squared plus 7. So an obvious polynomial in the numerator, obvious polynomial in the denominator. That said, we notice that 1 is a polynomial, a very simple polynomial, and so we notice that x can be written as x divided by 1 is a rational expression. As is 5 equals 5 divided by 1. And so we notice that all of our classic polynomials are also rational expressions. Rational expressions include all of our polynomial expressions as well. So first thing we're going to look at is evaluate the rational expression x plus 2 divided by x minus 3 at x equals 4, x equals negative 2, x equals 3, and x equals 10. Do it one more. Yeah, let's toss in x equals 2. We notice that x equals 4, we're going to get 4 plus 2 4 plus 2 divided by 4 minus 3 gives us 6 divided by 1 is 6. At negative 2, we're going to get negative 2 plus 2 divided by negative 2 minus 3 is 0 divided by negative 5, which is 0. And so you notice the numerator being 0 causes no trouble. We can let the numerator be 0 as much as we like. We just have to make sure the denominator isn't 0. At x equals 3, we get 3 plus 2 divided by 3 minus 3. Now that causes problems. That's 5 divided by 0, which is undefined. So we can't let x be 3. And we'll talk about that more in a minute. X equals 10. We get 10 plus 2 divided by 10 minus 3. So we get 12 sevenths. So that's an easy one. And then x equals 2. We get 2 plus 2 divided by 2 minus 3. So we get 4 divided by negative 1 is negative 4. So remember we mentioned that we can't let the denominator be 0. So we have what we call restricted values. we notice that values of x that would make the denominator 0 must be excluded from the domain. So this is pretty obvious in cases like x divided by x squared minus 1. We can write that as x divided by x minus 1, x plus 1. And so we can see that this is undefined at x equals 1 or negative 1. And so if we wanted to, we could say the domain is negative infinity up to negative 1, union with negative 1 to 1, union with 1 off to infinity. So anything except negative 1 or 1. Where it gets a little bit trickier is if we saw something like x squared minus x divided by 2x, we notice that something we're going to play with later on is the idea of simplifying these rational expressions. We can look at this as x times the quantity x minus 1 divided by x times 2, and we can simplify that as x minus 1 divided by 2, but we notice that that initial expression is undefined at x equals 0. This expression would be fine at x equals 0, but because it came from this original expression that had restriction at x equals 0, we have to specify that this equality is only true for x not equal to 0. So we notice that the main issue is that this equality is only true if x isn't 0. So when we do the simplifications, we're just indicating information that gets lost. So the x squared minus x divided by 2x is going to equal x minus 1 divided by 2 for any value of x except x equals 0. So this will usually be pretty straightforward. We're usually not going to do anything too complicated with that. So that actually brings us directly into the idea of simplifying rational expressions. We just saw a little bit of that with that common factor of x. We notice that a rational expression is simplified or in lowest terms if the numerator and the denominator have no common factors. So we notice that if we saw x divided by x plus 2, this is simplified. So I should say no common factors other than 1. Because you know, x and x plus 2 have a common factor of 1. But if we saw x squared minus 1 divided by x minus 1, we notice now we want to look at how we can factor that numerator. The numerator of factors is x minus 1, x plus 1, divided by x minus 1. And now we could also make it 1 times x minus 1. And so notice now we have a common factor. And so we're going to wind up getting x plus 1 divided by 1. And we don't have to write it as x plus 1. We don't have to write that 1 in the denominator. We can just say x plus 1 as long as x isn't 1. We have to pay attention to the fact that x equaling 1 for the initial expression causes problems. So we have to specify that this equality only applies as long as x isn't 1. So one thing to watch out for is if we had flipped that. If we had said x minus 1 divided by x squared minus 1 instead, is very similar. We're going to get 1 times that quantity x minus 1 divided by x minus 1, x plus 1, gives us 1 divided by x plus 1. We have to be careful that that's not x plus 1. We can't just bring that x plus 1 to the numerator just because we feel like it. We have the factor of x plus 1 in the denominator. We get a factor of 1 in the numerator. And so we're going to leave our final answer for that simplification as 1 divided by x plus 1. So you'll notice that we can have lots of factoring when we're dealing with these. If we saw something like x squared minus 4 divided by x squared minus 3x plus 2, we notice to simplify it, we have to factor everything. The numerator factors as x minus 2, x plus 2. The denominator factors as x minus 1, x minus 2. X minus 2 divided by x minus 2 is going to be 1 as long as x isn't equal to 2. And so we get x plus 2 divided by x minus 1 as long as x isn't 2. We notice x also can't be 1, but we can see that x can't be 1 from that denominator of x minus 1. So let's try something a little bit messier. If we had something like x cubed minus 4x squared minus 5x, all divided by x cubed minus 5x. That'll do. We notice, we'll make it 5x squared. We notice that we can write this as x times the quantity x squared minus 4x minus 5 divided by x squared times x minus 5. And so we notice that something you'll come across once in a while is even if you don't know what the factorization is, sometimes one of them will be easier and will suggest a factorization. So having that denominator x minus 5 suggests the numerator might have a factor of x minus 5. And so we try it. If we did x minus 5, we need x plus 1. And we notice we get negative 5x plus x is negative 4x, so that worked. So we notice the x minus 5's go away. X minus 5 divided by x minus 5 is 1. And we notice x divided by x squared, we're going to get x times x plus 1 divided by, we could write that x squared as being x times x. And so an x goes away. And we're left with x plus 1 divided by x. And again, we have to make sure we specify x can't be 5. We also need to be careful about factoring out negative 1s. We notice that if we saw something like x squared minus 5 divided by x squared minus 4 divided by divided by 2 minus x, we notice that we're going to get x minus 2, x plus 2, because it's a standard difference of squares, divided by the quantity 2 minus x, and so no common factor. But what you notice is that 2 minus x is the exact opposite of x minus 2, and so we can either eyeball it and just say, oh yeah, that's going to be negative 1 times x plus 2, or we can factor a negative 1 we can say x minus 2, let's write it this way. We could also write it as x minus 2 times x plus 2, and then in the denominator, we can factor a negative 1 out. We get negative 1 times the quantity x minus 2. And so now we get the x minus 2's going away again. We get x plus 2 divided by negative 1, and that also gives us negative 1 times that quantity x plus 2. So we have two options for how we want to construct that. We're always allowed to factor out a 1 or a negative 1.